So let's start with our traditional control charts. On a traditional control chart, what we have is upper control limit and the lower control limit, and then we have X double bar. But we know that all these UCL, LCL, and X double bar are calculated from the process. They are not set, they are not limits. They don't really mean anything in terms of the acceptability or the quality of the parts that are being manufactured or produced or the services are delivered. It doesn't say anything about the quality. It only tells us, those control charts only tells us if the process is under control or not. It's a statistical perspective on the processes. Is the process predictable? That's all the control charts can answer. But if your question is whether the process is under control or not, are my products or services that I'm creating, are they acceptable or not? Because they are two different independent things. Your process might be out of control, but all the parts that you're producing might be acceptable. Or the opposite is also true. Your process can be in control, but all the parts can be unacceptable. All right? That can be also a case. So CP and CPK measures the capacity and capability of the processes, and if the process is capable of producing good parts, and if it's capable, is it really producing good parts or not? It's a two-step approach to that question. Are we producing good parts or not? So in the first step, we have to analyze if we are capable. And on the second step, we have to answer the question, are we really producing good parts? And how are we doing that? For this, I represent it with charts, but you don't really need to create or you don't need to draw the charts to be able to answer that question. The answer to that question is very simple. All right, to answer to that question is upper specification limit minus, lower specification limit divided by 6 sigma hat. As long as this ratio is higher than or equal to 1, the process is capable of producing 100% good parts. So here your upper specification limit, here your lower specification limit, and this value in the middle is, it is your like target value, nominal value. If we have a manufacturing situation, if I'm producing parts, and if the design engineer created a dimension for a part, for a feature, something like that, let's say 10 plus and minus 1. Now this is a specification, all right? And here your target value from this information, your target value is 10, but you're okay with 9 and 11s, all right, as a production specification. Any production that is outside those specified limits are unacceptable. So in this case, for this example, your specification limit, lower specification limit is going to be 9. Your upper specification limit is going to be 11. And your target value is 10. But it is only going to make sense if we compare it with the actual production. All right, what is the actual production? Now, to be able to answer that, I have to go back to our process, actual production. What is happening? As you remember, those control limits, we have points on those control limits, right? Here and here, randomly distributed. But we know that they are averages representing the average of a subgroup. And a subgroup is made of maybe 1, 2, 5, 10, 50 observed samples. So in reality, they all have their own distributions. Each one of those subgroups have their own individual values in them, and all of them has a distribution something like this. So what I can say is the distribution of individual values, I can represent it from this point to this point, right? This is usually, not usually, always, the distribution of individual values is always larger, wider than the distribution of subgroup averages. The distribution of subgroup averages, we used to represent it with 6 sigma, right? This is 3 sigma plus and 3 sigma minus. But the distribution of individual values are represented by 6 sigma hat. And 6 sigma hat is what we use here in the formula. All right? So this distinction is very important. I think the biggest difficulty here is the comparison or the switch from the control charts to upper and lower specification limits. They are completely two different things. You shouldn't confuse, you shouldn't mix them, all right? I can't see my screen, but is any questions up to this point? Let me open the chat box. I think no questions so far. All right. So, upper specification limit, lower specification limit. How do we compare that? It depends on, again, we're comparing actual to desired, all right? So your engineer, your design engineer basically says that in our example, you are only allowed to the variation of 11 minus 9, 2 units. Let's call it a dimension, maybe 2 inches, all right? I'm going to make it more specific, 2 inch. 2-inch variation is allowed, all right? And then you have to compare this number, which is upper specification limit minus lower specification limit. You have to compare it, what is actually happening here. 6 sigma hat. Maybe this single value is, let's say, 8. And that single value is maybe 13. Okay, this side of my screen is not working. So, okay, this point maybe is 13. Now, what happened here is your variation, your distribution is 13 minus 8, and this is 5. 5-inch variation between all the available parts that I'm producing among the parts that I observed, right? So this is actually what's happening, and this is allowed. Again, there's one more point here. If you look at the subgroup averages, this is what we care for when we create a control chart, right? We look at the subgroup averages. As you see, all the subgroup averages are between the lower and upper control limit. This process is under control, but as you see, when I look in more detail to the individual values, and when I compare it with my specification limits, which is set by the design engineer, my variation is not acceptable. It's too high. Currently, even if my X double bar actual average is exactly at the same target value, let's say they're all aligned, they're all centered, many of my individual individual values are outside my specified limit. So the process is probably under control, not probably, the process is under control. That's what we can see from the control chart. The process is under control, but many of the parts are outside the specification limit, and I'm producing many unacceptable parts. And how do I say it mathematically? By checking that formula. Upper specification limit minus lower specification limit divided by the 6 sigma head. If this is greater than or equal to 1, we are happy. This is for the first step. I can say that my process is capable of producing 100% good parts. If your upper specification limit minus lower specification limit divided by 6 sigma head is less than 1, I can definitely say that some or many of those parts or processes or services are out of specification limits. All right? This is an undesirable situation if this happens. Is this first part clear? This first part is theoretical look into the situation. We didn't really compare the control charts or actual values to the specification limits at this step. So you might ask, what is sigma head? Sigma head has two formulas. There is one formula that you can use if you are given the range values, or there is another formula if you are given S value, standard deviation formula. If you are given the range values, sigma head is R bar divided by D2. R bar is something we know how to calculate. D2 is going to come from the fractions chart. All right. There are charts that we have been using for all those factors. Factor chart is going to help us to find that D2 value based on the size of the subgroup. All right. So let's say we passed that first step. We figured out that upper specification limit minus the lower specification divided by 6 sigma head is greater than 1. So what I can say is I can produce all good parts. But the second question is going to be, am I really producing good parts? I'm capable of producing good parts, but am I producing really good parts? To be able to understand or solve that second part, to be able to answer that second part, we need to compare our specification limit to what is really happening. We have to place them on top of each other. All right. So let's move that. Here we have our upper specification limit minus lower specification limit representing lines. So how are they compared? What is their location or position with respect to each other? I have to slide that upper specification, lower specification limit on my control chart and see exactly where they are located. All right. So when I move it up, they're gonna align. We're gonna align the X double bar to our nominal value, and let's say maybe, for example, our charts are lined up like something like that. Our upper specification limit is set here, lower specification limit came here. As you see, even though your Six Sigma head is smaller than allowed variation, they are not perfectly aligned. Because they are not perfectly aligned, some of the parts here in this region, actual parts, individual parts, will stay on the upper specification limit, above the upper specification limit. This is one way of failure, all right? Another failure can happen if your upper specification limit is somewhere here, let's say, and your lower specification limit is somewhere here. And now in this case, we know that there are parts here. So those parts are going to be below your lower specification limit. So there is an area that you cannot cover. Again, this is a process that is not producing acceptable parts. All right. A third case can be on both sides. Maybe your upper specification limit and lower specification limit is something like that. So there are parts over here unacceptable, and there are parts here that are above and below your specification limits. And this is the graphical representation of three situations that can happen. And how do we test them? The formula is, again, simple. Upper specification limit minus X double bar divided by 3 sigma head, and X double bar minus lower specification limit divided by 3 sigma head. We calculate both of them. All right, we calculate both of them. If both of them are greater than or equal to 1, all my parts are acceptable. So probably your graph is something like this. On both sides, you're covering every individual part. If any of those terms is less than 1, not equal, if less than 1, it means that we are producing bad parts. On which side we are producing bad parts, depending on, of course, which side is smaller than 1. If this is smaller than 1, then it means that you have that situation. All right, this situation. You have parts above your upper specification limit which cannot conform to specifications. If you have this less than 1, then your parts are unacceptable on the lower specification side. All right. So we want both of them to be greater than or equal to be 1. If they are less than 1, if any of them is less than 1. We have too many C's, acceptable parts or services.